just a moment ago, I saved the work. We're looking at exercise 2, but a moment ago we found the limit of x to the x. I wanted to save that work here and do exercise 2, part A right here. Part A, by the way, says take x to the x and find its derivative, right? So what we actually do is this. There's the variable is in the base and in the exponent, so we'll set y equal to that. Hope that sounds familiar. Did it here in part H in the previous exercise. So then we'll apply ln to both sides. L on the left side, L on the right side. Okay? And then we'll make sure I'm doing the, yeah, that is the part I called. Then, just as we did before, we'll take that x here and bring this in front using the laws of logarithms. Ln of y is equal to x times ln of x. Here's where things will look different. Over here, we took a limit on both sides. Right? From this equation, we limit on both sides. Here, the question's about a derivative. So let's take a derivative on both sides. We're going to do an implicit differentiation. So I like to write a d over dx on there, just as a reminder. Y, by the way, is a function of x. So when you differentiate ln of y in implicit differentiation, together with the chain rule, you'll have a 1 over y times the dy dx. On this side, when you differentiate, look, this is a product. X times ln of x. No times there. This is ln of x. X times ln of x. The derivative is going to require the product rule. So don't use the fake product rule. Make sure you do first times derivative of second. First times derivative of second plus the second times the derivative first. The derivative of x is 1. Okay, so that's the product rule. Remember, there's a plus, you know, there's this, the product rule has pieces to it. By the way, if we were asked about finding the derivative of x to the x, or we were asked about finding the derivative of y, well, that's what this is, dy over dx. So we need that by itself, but there's a 1 over y. So let's multiply both sides by y. We have dy over dx is equal to y times this quantity here. Right, x times 1 over x plus ln of x. I just won't write the times 1. And then all we have to do to finish this is what we need. Just let's rewrite this, and the question up here never mentioned y, so let's just replace the y here with x to the x. So x to the x times what was here. Oh, we can simplify this. X over x is a 1 plus ln of x. Okay, great. That's part A. The point is, these 3 steps right here are the same as these 3 steps right there. The difference is, and look, same form of function, right? It's just the function was x to the x. The difference was take a limit on both sides here, take a derivative on both sides here. So let's take a look at part 2, or part B. It's part B. So it says find the derivative of x to the 1 over x. Look, same deal, right? So the reason these questions were organized right next to each other where they were. So let's say that y is x to the 1 over x. Well, ln both sides. And why don't we already just bring that 1 over x in front, right? And now we're going to differentiate both sides. Okay, so this used to be an ln of x to the 1 over x. That 1 over x came in front. Implicit differentiate on both sides. 1 over y times dy dx, or y prime. Differentiate here using the product rule. So the first times the derivative of the second. Derivative of 1 over x is 1 over x. Oh, this 1 over x is just copying that one. Plus the second ln of x times the derivative of x to the negative first. So that'll be a negative x to the negative second. Okay, to get y prime by itself, we just need to multiply by y on both sides. So that y that we multiply, we could write a y here. But why don't we already just write an x to the 1 over x there, and then this needs to be copied in here. Let's simplify as we do it. 1 over x times 1 over x is 1 over x cubed, or x squared, excuse me. And then this could be written as a plus, or I guess a minus, sorry. This minus, not affected by the exponent. So minus ln of x in the numerator, and how about instead of x to the negative 2 in the top, let's write an x to the positive 2 on the bottom. So that's one way to write the final answer here. So I hope it's helpful to see kind of how many problems in a row that deal with this ln technique. Okay, what do we have next? Part C. Just good old derivative reminders here. Ooh. So look, for part C, I think it's going to be nice to think of the function we have by doing the following, right? Let's draw an extra set of parentheses. And do you see that x to the 6th, 8 to the x sine of x? X to the 6th, 8 to the x sine of x. So it'll be helpful to just draw like maybe an additional set of parentheses, because this is going to be the product. It's a triple product. We'll need the product rule twice, actually, so I think it's helpful to organize it like that. Plus we'll just write the rest of this, arc tan of x, or equals, write this as tangent inverse of x over ln of 4 plus 8x. All right, here you go. So what's y prime? Well, this is a product, right? So first is this, second is that. So we've got the first, x to the 6 times 8 to the x, times the derivative of the second, and the derivative of sine of x is cosine of x. Plus the second, sine of x, times the derivative of the first. So we need to differentiate x to the 6 times 8 to the x. Now sometimes what happens is, people are in a good habit of product rule. And then right here they'll say, oh, x to the 6 times 8 to the x. So I'll just differentiate x to the 6 and 8 to the x separately and stick the results, multiply together. But that's not the product rule, right? So when differentiating this here, maybe if I will circle or underline this in green, we need the product rule there. Right? So the derivative of what's underlined in green requires the product rule. It will be the first, namely x to the 6th, times the derivative of 8 to the x, which is 8 to the x times ln of 8, plus the second, 8 to the x, times the derivative of the first, and that's the derivative of x to the 6th using the power rule, 6x to the 5th. Okay, that's the first term. I don't think I'm going to have room for the second term here, so I apologize. That plus, right, use the sum rule. We need to differentiate that fraction using the quotient rule. So we don't differentiate the top and bottom separately. That's what we do if we were applying L'Hopital's rule, but that's not what's going on here, right? We're not finding a limit. We're doing a derivative question. Okay, so bottom times the derivative of the top, so ln of 4 plus 8x. Times the derivative of the top, the derivative of arctan of x is 1 over 1 plus x squared. Okay, minus the top, arctan of x. Times the derivative of the bottom. Ooh, okay. So the derivative of ln of 4 plus 8x is going to require the chain rule. Right? So outside prime of inside. So 1 over inside 4 plus 8x times the derivative of the inside. So the derivative of 4 plus, well, 4 differences is 0. 8x differences is 8. Okay. So all of this, so 1d high minus 1d low. Yeah, all over the denominator squared. So ln of quantity 4 plus 8x squared. Okay, there's part C. Should we look at part D? All right, so part D. So 2 to the arc sine of x to the 6th. Right? So we'll just already write y prime here. So 2 to the, oh, you know what? There's a chain rule inside a chain rule, huh? So 2 to the x differentiates 2 to the x ln 2. So that 2 to the x is going to get replaced with, and you compose with this arc sine of x to the 6th. Oh yeah, times the ln of 2, that's part of the derivative rule of 2 to the x. But now, due to the chain rule, we need to differentiate arc sine of x to the 6th. Well, the derivative of arc sine of x is 1 over root 1 minus x squared. But that x gets composed, we compose in this x to the 6th. And then due to the next chain rule, we need to multiply by the derivative of that, the inside, the x to the 6th, which will have a 6x to the 5th here. Okay, that's the first term. And then after a minus sign, so sorry for the spacing, but after a minus, the derivative of a log base 3 of something. So it'll be a 1 over ln of 3, we'll just write it this way, times normally a 1 over x. But again, due to the chain rule, it's going to be 1 over the inside. So 5x to the 5th plus secant of x. Okay. Times, now, due to the chain rule, we need to differentiate the inside, and we're staring at the inside right here, right? So we'll have here 25x to the 4th plus the derivative of secant x, so secant x tangent x. So that, oh, and then it ends with a plus e to the x. That's not inside the log, so we need to differentiate e to the x, which is, fortunately, just itself. That's part D. Part E, so we're supposed to take this equation, sine of x squared y to the 4th plus xy plus 5 equals x minus y plus x squared plus 2 to the x, and find dy dx. Y depends on x. So we're going to implicit differentiate. So we're going to do a derivative with respect to x on both sides. On the left side, here, when we differentiate, sine of a messy thing, so this is going to be a chain rule, right? So cosine of the inside times the derivative of the inside. Well, x squared times y to the fourth is product, so we need to use a product rule. So we'll have the first times the derivative of the second. Y to the fourth will differentiate to 4y to the third times, due to the implicit differentiation, dy dx. Okay, plus the second y to the fourth times the derivative of the first times the 2x. Okay, plus, ooh, there's another product, x times y. So we better apply the product rule when differentiating. So that plus is right there, right? So first times the derivative of the second, well, the derivative of y is the derivative of y, plus the second times the derivative of, the derivative of x is just 1, so times the 1, which is not 1. Plus the derivative of 5, which is 0, so let's not write a plus 0. On the right side, the derivative of x with respect to x is 1, minus the derivative of y with respect to x is the derivative of y with respect to x. Plus, like, no more funny business, these are nice. The derivative of x squared with respect to x is 2x. And the derivative of 2 to the x with respect to x is 2 to the x times ln of 2. What's left to do? We need to get dy dx. So where's the dy dx? It's right here, right there, right there. So let's get all those terms on one side. How about all on this side? Right? So we take this and distribute to this term and to this term. There's going to be a dy over dx times x squared times 4y cubed, and then times, we have to distribute the cosine of x squared y to the fourth. We're also going to have this when we distribute this times that, but there's no dy dx, right? So cosine x squared y to the fourth times y to the fourth times 2x, a term without a dy dx. So let's subtract that on both sides. So somewhere over here, we'll have a negative cosine of x squared y to the fourth times y to the fourth times 2x. So that accounts for, we've distributed. One of these is written here, just with a shuffled order. The other is written over there because we subtracted on both sides. Then there's this. So we want x times this. You know what? Let's factor out dy dx. So when we factor out a dy dx, this term will be written just as a plus. Think about how this would distribute to this term and to this term. There's a y that doesn't have a dy dx, so let's subtract y on both sides. There's a 1. Let's leave that on this side, so plus 1. There's a minus dy dx, so let's add that to both sides. And if we do a plus dy dx and factor out, there's going to be a 1 for that. There's 2x, we'll leave on this side. 2 to the x ln 2, we'll leave on that side. That accounts for, I believe, if I didn't make a mistake, all terms on all sides. And then dy dx is just going to be this divided by that. Okay. Let's see. Oh, yeah, let's take a look at parts F, G, and H. All right, so F, G, and H. So part F, so find dg dx if g is equal to integral 3 to the arc sine of x of 6t cubed dt. So what we need to do here is replace that with like a u or something, right? So we'll have u is arc sine of x. So g is rewritten as integral 3 to u of 6t to the third dt. Now to find dg dx, the derivative of g with respect to x, according to the chain rule, is the derivative of g with respect to u times the derivative of u with respect to x. So dg du, well, here's g. We want to differentiate this, and we needed just a single variable to do that. So by the fundamental theorem of calculus, we take the function that's written here. Basically, we take this function, we want to write it here, except we replace every t with a u. So look at 6t cubed. We'll write that here, but replace every t with a u. It's just how FTC1 looks. Then we need du dx. So differentiate arc sine of x. We'll write that here. That's 1 over root 1 minus x squared. Now the last thing to do is replace the u here with arc sine of x. So we'll have we can drop the parentheses. 6 times arc sine of x, and that was what u was. But then, oh, there's a cube, so let's do that cubed times 1 over root 1 minus x squared. Part G, find dg dx if g is equal to integral from x to 3 of ln of 4 plus t to the 4th dt. Okay, so another way to write g, it's helpful if the variable is on top and the constant is on bottom. That's just how FTC1 looks. So we'll swap these two, put the 3 down here, the x there. There is a cost to that, and it's having a minus sign. If you want, you can stick the minus sign inside. Well, let's just do that, just for funsies. Minus ln of 4 plus 2 to the 4th dt. So then dg dx. Good thing there's an x already there. We don't have to go through a chain rule process here. It's going to be this function that we see right here, this function here, including with the minus sign. So the derivative of the integral of a function, like the function underlined in red, is going to be that function, just rewritten using the right variable. So the point is, what's underlined here, we're going to write it here, just replace every t we see with an x instead. Negative ln of 4 plus x to the 4th. So the derivative we were asked to compute, the derivative of g, cancels with the fact that the first part of g, its definition, talked about integral. So derivative of integral of function is the function. Finally, part h is a by definition. So we're asked to take f of x equals 5x squared and find f prime of x by definition. So let's do that. F prime of x is, well, this is a limit, right? Limit h approaches 0 of f of x plus h minus f of x all over h. Maybe just a quick reminder that what was going on there was you just have some function in general, right? So your y equals f of x. The minimal piece of info you need to remember is 2 points end up creating a secant line, and all that absolutely has to be remembered. The minimal amount to remember about this is you have like maybe an x coordinate here called a, and then that distance here is called h. So have that picture in your mind. All the other pieces, that's the minimal amount to have remembered. The rest of it you can build, right? So if this much is a from here to here, that's why there's an a tick line. That much is h. This has got to be a plus h. And then the y value, if the x value is a, and the point here is on the curve, y equals f of x, this has got to be f of a. And then here, if the x coordinate is a plus h, the y coordinate here has got to be f of a plus h. So the slope of this line here, right, so what's the slope of this secant line? It's got to be change in y over change in x. The y coordinate, this minus that, f of a plus h minus f of a, all over this x minus that. So a plus h minus a simplifies to just an h, right? But you got a plus a and a minus a. Take care of those. So that's the slope of the secant line, and that's all that appears right here. Oh, just, sorry, with instead of a's with x's, okay? But that's what appears here. That's the slope of the secant line. The derivative, though, is the slope of the tangent line, meaning we want this gap to shrink. We want this tick mark to get closer to that tick mark. So h gets closer to 0. That's why there's this. Okay, so let's go ahead and compute this. Limit h approaches 0, f of x plus h. Well, f of a thing is 5 times the thing squared. So f of this thing, x plus h, is 5 times x plus h quantity squared. F of x, just get the copy of that. Now, sometimes the temptation is for people to try to distribute the 5 first, but you can't because of the square, order of operations. We've got to take care of x plus h times x plus h first. Limit h approaches 0, just copy the 5, x squared plus 2xh is h squared minus 5x squared, still right there, right, copied, over h. You distribute the 5, limit h approaches 0, say 5x squared plus 10xh plus 5h squared. minus 5x squared all over h, right? Plus 5x squared minus 5x squared. Limit h approaches 0. Look, all we're left with in the numerator are these two terms. Just a step ahead, thinking 2 steps ahead, we're going to want to cancel with that h. So why don't we factor out an h in the numerator? But h times the quantity 10, x, okay, that h was factored out, plus, let's see, h times something is 5hh. So that's a 5h here, right? H times 5h is 5h squared. All over h, we get a cancellation. So we have limit x approaches 0 of, after the cancellation, just what's in parentheses there, 10x plus 5h. I get there's two variables here, x and h, but x was just like an unknown. The variable for the limit problem is h, so this is a polynomial. And by the direct substitution property for limit of a polynomial, we can plug in 0 for the h and have here 10x plus 5 times 0, or, well, plus 0, right? So just 10x.